Hello everyone, greetings from ACE Engineering Academy and ACE Online. Myself Professor Rajendra Garashe, and in this video or in this session we are going to discuss about some important questions and some important concepts related to the subject power electronics, TS SPDCL assistant engineer, right, EEE batch. So friends, if you check the previous year question papers, surely you will be getting around 8 to 10 questions related to this subject. Okay, 8 to 10 questions I am saying. So first of all, let us discuss the syllabus. What are the important topics, and specifically today we are going to discuss DC to AC converter, and if the time permits we will discuss about DC to DC converter as well, right? Yeah, so let us start. So this is the syllabus. Characteristics of semiconductor power devices, and in a semiconductor power devices they have given diode, thyristor, triac, GTO, MOSFET and IGBT. But as long as the syllabus is considered, most of the points will be related to the thyristor only, right? Thyristor is a family of devices. In that the most popular member is the silicon control rectifier, right? Yeah. And whereas other devices you are having like only introductory part. Definitely in the examination also you will get most of the questions related to the SCR, silicon controlled rectifier. Second is DC to DC converter. In that they have given buck boost and buck boost converter. Next, line commutated thyristor based converters, bidirectional AC to DC voltage source converters. It is AC to DC converter. Issues of line current harmonics, right? Which harmonics are present in the source side current. Next, power factor, distortion factor for AC to DC converters. Next, single phase and three phase inverters, and they have given only sinusoidal pulse width modulation. But if you refer the previous year question papers, they have asked the questions on single pulse width modulation, right? So here single pulse width, multiple pulse width as well as sinusoidal pulse width we need to study, right? So specifically in the syllabus they have mentioned only power semiconductor devices, DC to DC converter, AC to DC converter, that is the rectifier, and DC to AC converter, that is the inverter. But in addition to this you need to prepare AC voltage regulator, also cycloconverter, and some small part related to the fundamentals of electrical drives. Okay, they have not mentioned here, but they have asked the questions based on those three topics as well. Okay, so summarizing the chapters. So first is power semiconductor devices. This chapter deals with study of semiconductor devices like power diode, transistor family devices like power BJT, power MOSFET, IGBT, thyristor family devices like silicon control rectifier, GTO, triac, etc. Okay, right. So this is the chapter number 1. Regarding the first chapters, silicon control rectifier contents are very important. Okay, right. Second, AC to DC converters. In this we are having the uncontrolled rectifier, controlled rectifiers, single phase as well as three phase. Okay, right. In a single phase again there are half wave rectifier, full wave rectifier, midpoint rectifier, bridge rectifier, midpoint configuration, bridge configuration. Similarly in case of three phase rectifiers we are having a three phase half wave, three phase full wave rectifiers. Also in single phase and three phase we are having the semi converters. In addition to that, effect of source inductance, right? Input power factor for RL load, RLE load. If the load is highly inductive, how to find the input power factor, right? Input power factor is a distortion factor into displacement power factor, etc. Right? So next, DC to AC converters. This chapter specifically we are going to discuss today. Okay, it is also known as a inverter. In this chapter, the important points are single phase half bridge inverter, single phase full bridge inverter with R load, L load, RL load. Okay, right. As long as your examination is considered based on the RLC load, they have not asked the question. Okay, right. But R, L and RL are important. Similarly, single phase full bridge inverter. Next important points are what is the waveform nature, whether it is a sinusoidal or cosinusoidal, or it is a square function, or it is a cosine square function, which harmonics are present, etc. Three phase inverters, 180-degree conduction mode, 120-degree conduction mode, right? Nature of phase voltage, that is load phase voltage, load line voltage, which harmonics are present in a phase voltage, which harmonics are present in a line voltage. Apart from that, pulse width modulation technique, single pulse width modulation, multiple pulse width modulation and sinusoidal pulse width modulation technique, right? Next, in order to remove the particular harmonic, what is the required pulse width in a single pulse width modulation? Like this they have asked the questions, okay, right? And at the end we will discuss the current source inverter. Next, if the time permits, we will focus on DC to DC converter as well. Okay, in DC to DC converter, very less points are there. Step down chopper, step up chopper, step up, step down chopper. We modified these basic chopper circuitries because the chopper circuitries are having some drawbacks, and after modifications those are renamed as buck converter, boost converter and buck boost converter. Apart from that, voltage commutator chopper and current commutator chopper. That's it. Only 8 points you are having, okay, in DC to DC converter. Next, AC voltage regulator. AC to AC converter, in that one is the AC voltage regulator. AC voltage regulator, input frequency, output frequency both are same. It converts fixed AC to variable AC. But at the output side, variable AC means variable in terms of only voltage. Output side frequency is same as that of the supply side frequency. Okay, so it gives the frequency constant, but output voltage is varying. Okay, it is a controlled output voltage, you can say, right? Whereas DC to AC converter, output is variable voltage, variable frequency. This one is variable voltage, constant frequency. Cyclo converters, this is also AC to AC converter. It gives output in terms of variable voltage, variable frequency, right? AC to AC converter, input is also AC, output is also AC, but output side voltage as well as frequency both are variable. So in one of the examination they ask the question, which of the following converters are or gives variable voltage and variable frequency output? So variable voltage, variable frequency means DC to AC converter as well as cyclo converter. AC voltage regulator, it will not give the variable frequency, be careful, right? In cyclo converter we are having the different types, step up cyclo converter, step down cyclo converter, right? In that step up cyclo converter require the forced commutation, whereas step down cyclo converter the natural commutation is used. Like this they have asked the question, okay, right? Next, fundamentals of the drives, only some small fundamental introductory part of the drives is there. Okay, so these are the 7 chapters. In that you will find the most of the questions on these 4 chapters. Most of the questions are on these 4 chapters. Okay, right. So now we are going to discuss DC to AC converters, right? So DC to AC converter means it is the circuitry which gives fixed DC to variable AC. It converts fixed DC input to variable AC output. Fixed DC to variable AC. Variable AC, that is variable in terms of voltage and frequency. Variable voltage and variable frequency. What is the expected output from the inverter? Yes, can anyone? Suppose you have gone to the market to purchase the inverter, right? What are your expectations from that inverter? Let us consider single phase inverter. Yes, can anyone? What is the expected output of a inverter, single phase inverter? Yes, expected output of single phase inverter. Inverter should give which type of the output? Sinusoidal, cosinusoidal, square. Yes. Yeah, Ashwini, you are saying it is a square. If my expectation is square waveform, okay, means it is like my inverter is fulfilling my requirement. Practical inverters are fulfilling requirement, but my expected output is my inverter should give the sinusoidal output, na, right? Whatever the electricity we are getting from electricity board, that is a sinusoidal supply, the same we expect from inverter, right? So my expected output from the inverter, it should be sinusoidal, right? Inverter should give sinusoidal output. This is my expectation. But our practical inverters are not giving the sinusoidal. They are giving the output in terms of square function, quasi square function, stepped function, etc. Okay, right. So my expected output is a sinusoidal, right? Next, so classification of inverters. So inverters are classified based on, first is nature of input source. So based on the input source, there are two types. One is voltage source inverter, second one is current source inverter. VSI, voltage source inverter, and CSI, current source inverter. Voltage source inverter and current source inverter, right? What is the difference between these two? In voltage source inverter, the input voltage to the inverter is a constant. Input voltage is a constant, right? And in current source inverter, the input current to the inverter is a constant. Here input voltage is constant, here input current is a constant. All right? Yes. Second classification is based on circuit configuration, or it is known as a based on the connection. Okay. So based on connection, there are types like series inverter, parallel inverter, and bridge inverter. In bridge inverter, again there are two types, half bridge and full bridge. Half bridge and full bridge. All right. Third classification is P, is pulse width modulated inverter. Pulse width modulation type inverter. Okay, right. Square wave, quasi square wave, and PWM. Right. Yeah. Next, so this is about the classification of the inverters. Now we are going to discuss the difference between VSI and CSI. One difference we discussed, in voltage source inverter, input voltage is constant. In current source inverter, input current is constant. Okay, so in CSI, input constant DC current is there. That is, input current is constant. Whereas in voltage source inverter, input voltage is constant. Input is a constant DC voltage, na, right? So constant DC voltage means input is a constant voltage. Here input is a constant current. All right. Next, in current source inverter, the feedback diodes are not required. Right. Here feedback diodes are not used or not required even. Keep in mind, In case of rectifier, whatever the diodes we are using, in RL load specifically we use the diode na, and those diodes are known as a freewheeling diode. Whereas in inverter, whatever the diode we are using, those diodes are known as a feedback diodes. Those diodes are known as a feedback diodes. Why those diodes are known as feedback diodes? Because in inverter circuitry, through the diode, your load feeds to the source. Through the diode, your load is supplying to the source. Load is supplying energy to the source, right? So load is feeding back the power to the supply. So that's why it is known as a feedback diodes, right? Here feedback diodes are not required in current source inverter, whereas in voltage source inverter the feedback diodes are required. Feedback diodes are required. Okay, next, in current source inverter the thyristors are used, means generally the current source inverters are preferred for capacitive load. Next we will discuss for the capacitive load, those are preferred. And if the load is capacitive and if we use the thyristor, then in order to turn off the thyristor, here we did not to go for additional commutation circuitry. The circuit which is used to turn off the thyristor is known as a commutation circuitry. Here I am saying in current source inverter the thyristors are used. Why? Generally the current source inverters are preferred for capacitive load, and if the load is capacitive, even though if I use the thyristor, in order to turn off the thyristor, I need not to add, I need not to go for the forced commutation circuit. Means for turning off of thyristor, additional elements are not required. So that's why here thyristors are preferred, right, in CSI. But whereas in voltage source inverter, fully controlled switches are preferred. Fully controlled switches, right? So here fully controlled switches are power BJT, IGBT, power MOSFET, GTO, right? Fully controlled means you can check power BJT is a current control device, right? If my base current is greater than some specific value, my BJT will turn on. If I remove the base current, my BJT will automatically turn off, right? Immediately it will come back to the off state. So in order to maintain BJT in a on state, I need to circulate the base current continuously. If I remove base current, my BJT will turn off, right? Similarly, IGBT is a voltage control device, right? We are having MOSFET, it is also voltage control device. These are also fully controlled switches. GTO, positive gate current, turn on the GTO. Negative gate current, turn off the GTO, right? So all these are the fully controlled devices. But whereas your thyristor in the sense SCR, silicon control rectifier, whether your thyristor is a fully controlled device, no. I can turn on the thyristor by circulating the gate current or positive gate current. But if I remove the gate signal, suppose my thyristor has turned on by using the gate signal, and if I remove the gate signal, whether my thyristor will come back to the off state? No, thyristor will not come back to the off state. So thyristor is a, or SCR is a semi-controlled device, whereas all these are fully controlled devices. Okay, so fully controlled devices are used in a voltage source inverter. If I use thyristor here, in order to turn off the thyristor, I need to go for additional circuitry known as a commutation circuitry. Okay, right. But here commutation circuitry is not required. Here your thyristor turns off due to this nature of the load, Okay, next, output current. Yes, important conclusion. They have asked the question. Okay, in current source inverter, output current is independent of nature of load. Output current is independent of nature of load. Whereas in voltage source inverter, output voltage or load voltage is independent of nature of load. In voltage source inverter, for all type of the loads, my load voltage is a square waveform only. In current source inverter, for all types of the loads, my load current waveform will be square wave only. Here load current waveform is independent of nature of load. Here load voltage waveform is independent of nature of load, right? Yeah, next, load voltage depends on load, right? Next we will discuss as we proceed. Here load current depends on load. Load current depends on load, right? Yes. Next, current source inverter is generally preferred for capacitive loads, whereas voltage source inverters are preferred for inductive type of the loads, R, RL, L, etc. Okay, these are preferred for capacitive. These are preferred for inductive type of the loads, right? Inductive type of the loads. So these are the differences between voltage source inverter and current source inverter. Next, now we are going to discuss a single phase half bridge inverter, right? Single phase half bridge inverter. Let us consider the load is a purely resistive. This is a circuit diagram for single phase half bridge inverter. In a half bridge inverter, a specially designed 3-wire DC supply is used, right? So check here, this is my total DC supply. Total available voltage is V by 2 plus V by 2 means V volt is available, right? But that total voltage is divided as this is V by 2 and here it is V by 2, right? So this is a DC supply, but it is having a 3 wires, 1, 2 and 3, right? So in a half bridge inverter, a specially designed 3-wire DC supply is used or it is required, right? Next, here we are using 2 switches S1, S2. These 2 switches are fully controlled switches. This can be power BJT, this can be power MOSFET, IGBT or GTO, etc. Right? Right. Next, across each switch a diode is connected in anti-parallel. These diodes are known as a feedback diodes and load is a resistive. As long as the resistive load is there is a no operation of these diodes D1, D2. For resistive load, there is a no operation of the diodes, no operation of diodes, right? Now, here IZ1, IZ2. IZ1 indicates controlling signal to the switch S1. IZ2 indicates controlling signal to the switch S2. Okay, so here during t equal to 0 to t by 2, t equal to 0 to t by 2, we are applying the controlling signal to the switch S1. So if I apply the controlling signal to the switch S1, suppose this is your power BJT for example, okay. So in case of power BJT, this IG1 will be your IB1, that is a base current, right? We know power BJT or BJT is a current control device. Which current controls the BJT? Base current, alright. So if S1 and S2 are the BJTs, then here IG1, IG2 are nothing but IB1 and IB2, okay. So here during 0 to t by 2, during t equal to 0 to t by 2, we are applying the controlling signal to the switch S1, alright. So therefore my switch S1 will be in a conduction mode. During 0 to t by 2, S1 will be in a conduction mode. Next, current will be flowing like V by 2, S1, load and again back to the V by 2. Like this the current will flow, okay. You can apply KVL to the loop, you will get V0, this is my V0 na, right. V0 is equal to V by 2. So during 0 to t by 2, my switch S1 will be in a conduction mode. Here switch S1 will be in a conduction mode. And what is output voltage? It is a V by 2. Alright. Next, what is the output current? According to Ohm's law, we know V0 is equal to I0 into R. So if my V0 is a V by 2, what is I0? It is V0 by R na, that is V by 2R. So therefore, my I0 is a V by 2R. Check here, V by 2R and this is V by 2. Right? During 0 to t by 2, only switch S1 will be in a conduction mode. Now what is happening at t equal to t by 2? I am removing the controlling signal of switch S1 and I am applying controlling signal to the switch S2. So tell me, if my S1 and S2 are the fully controlled switches, as soon as I remove the controlling signal, my respective switch will turn off, right? Respective switch will turn off. Now I am applying controlling signal to the switch S2. So S2 will turn on. How the current will flow? Current will flow like this, V by 2, load, S2 and again back to the V by 2. Alright, like this the current will flow. You can apply KVL, you will get V0 is a minus V by 2 and I0 is minus V by 2R. So V0 is a minus V by 2, negative pulse, and I0 is minus V by 2R. Which switch conducts here? Here switch S2 conducts. Right, and after capital T again the same cycle will repeat, alright. Next, so tell me, my input voltage is a DC na, it is a constant voltage, but my output voltage is positive, negative, positive, negative. It is a DC or AC? It is having two values na, positive, negative means it is a alternating voltage, right? It is a AC output. But whether it is a sinusoidal? No, it is not a sinusoidal, it is a square waveform. My expectation is sinusoidal, but my practical inverter is giving square waveform. It is not sinusoidal, right? So therefore this waveform consists of different harmonics, right? And by using the tool, that is a Fourier series analysis, okay, with the help of Fourier series, we are analyzing this waveform and we are concluding which harmonics are present in this waveform, okay, right? So this Fourier series analysis is important. Means derivation is not required, but final conclusions are important as long as this chapter is considered, okay, right? Now, yeah, so here can we write V0 RMS value of output voltage. For square function, the RMS value is nothing but amplitude. It is a V by 2. What is I0 RMS? V by 2R. I0 RMS is equal to V by 2R. Right? Similarly, we can find the load power. It is equal to V0 RMS into I0 RMS. It is V square by 4R. V square by 4R, etc. Right? So this is the half bridge inverter. My half bridge inverter is giving square waveform, right, as a output. So if you check, based on the nature of wave shape of the output voltage, this is giving square wave, na? So that's why this inverter is also known as a square wave inverter, right? Based on the nature of input is DC constant voltage, na? Right? Input voltage is constant, right? So therefore it is also known as a voltage source inverter, okay? So this is a voltage source inverter. That's why here I have written VSI, that is voltage source inverter. And based on the wave shape of the output voltage, it is a square, right? It is a square wave inverter. And based on the connection, it is half bridge inverter. It is a half bridge inverter. All right. Next, so here there are some demerits of half bridge inverter. It requires specially designed 3-wire DC supply. Second is output voltage magnitude is Vs by 2 only. My total available voltage is V by 2 plus V by 2, that is total available voltage is V, na? But in output I am getting V by 2 and V by 2, means my source utilization is only 50%. So here source utilization is only 50%. And also for R load, for resistive load, there is no functioning or no operation. There is no operation of feedback diodes. No operation of a diode for resistive load I am saying, okay, but for inductive L load, RL load, your diodes will be there in a picture, right? Yeah. So important points: output voltage square function, output current square function. V0 RMS is V by 2, I0 RMS is V by 2, okay, right. Next, Fourier series analysis, okay, I am writing direct expression here. This is my output voltage waveform, right? So for this waveform, the Fourier series expression is summation over n equal to 1357 up to infinity 2 Vs by n pi into sine of n omega t, okay. Before this, we are having some derivation, okay. Here I am directly putting the final results. If you want the derivation, I will share the notes, okay. Please message me. At the end of this session, I will give the contact number, right? Yeah. So here the important points are summation over n equal to 1, 3, 5, next will be 7, 9, 11, 13 up to the infinity, and we are having this expression. So what this indicates? It indicates my output voltage is having only odd harmonics, right? This is a fundamental third. N is equal to 1 means fundamental component. N is equal to 3 means third harmonic component. N is equal to 5 means fifth harmonic component. N is equal to 7 means seventh harmonic component, etc. Okay. So always keep in mind, if you are having the square waveform, na, then in that waveform only odd harmonics will be present. That is, even harmonics will be absent. Only odd harmonics. Only odd harmonics will be present. Even harmonics will be absent, right? Even harmonics will be absent. Next, now from this expression, we can write the output voltage at fundamental frequency. Okay. Yes, let me write here. Yeah, I am writing here. Output voltage at fundamental frequency means V01. Please listen. V01 indicates output voltage at a fundamental frequency. Means in this expression, simply put n equal to 1. What is n for n equal to 1? I will be getting 2 Vs by pi into sine of omega t. So it is 2 Vs upon pi into sine of omega t. This is output voltage at fundamental frequency. Output voltage at fundamental frequency. So you can refer the previous year question papers. They have directly asked the expression for output voltage at fundamental frequency. Okay, output voltage at fundamental frequency. At fundamental frequency. Output voltage at fundamental frequency. All right. Now tell me, fundamental frequency output voltage is a sinusoidal, na? Yes or no? This is a sinusoidal function, right? So this is a sinusoidal function V01. That is fundamental frequency output voltage is a sinusoidal function. Now can I say that this is 2 Vs by pi? This is 2 Vs by pi. It indicates peak value of this V01. Yes or no? Right? We know V equal to Vm into sine of omega t. That Vm means peak value, na? So similarly here, before sine we are having this 2 Vs by pi. So can I write peak value of output voltage at fundamental frequency? That is V01 peak, which is equal to 2 Vs by pi. 2 Vs by pi. That is V01 peak. Now from this, can we find V01 RMS? Yes, V01 RMS for any sinusoidal waveform, RMS value is peak value upon root 2, right? So therefore it is V01 RMS is equal to V01 peak by root 2, that is 2 Vs by pi upon root 2. So 2 Vs by pi by root 2 means it will be like root 2 into Vs upon pi. Root 2 into Vs upon pi, right? Yeah. So this expression root 2 Vs by pi, this is important. V01 expression 2 Vs by pi sine of omega t, this is important, right? V01 RMS, V01 peak and V01 expression. Which harmonics are present? Only odd harmonics are present. Only odd harmonics are present. All right. Next. Similarly, can we write the expression for current waveform Fourier series expression? Yes. Current waveform is also square function, na? Like your voltage waveform. Okay. So here I am writing the expression. Check. 2 Vs by n pi into Zn into sine of n omega t minus phi n. This is in general I have written. But if the load is resistive, then what will happen? Here I am writing. Where Zn is equal to under root r square plus n omega l bracket square. And phi n is equal to tan inverse of n omega l by r. N omega l by r. Right? Now tell me, for resistive load, if I want to find the value of Zn and value of phi n, right? So in this case, what we need to do? For resistive load means only R is present, na? What about the inductor value? 0, right? If inductor value is 0, this n omega l will become 0. So what is my Zn? Zn is equal to under root r square plus 0, na? So it is like under root r square. Under root r square means r. So my Zn is equal to r. And what is phi n? Phi n equal to tan inverse of n omega l by r. What is L? L is 0, na? Because purely resistive load. So it is like tan inverse of 0 by r. Tan inverse of 0 by r means it is like tan inverse of 0. Tan inverse of 0 means 0, na? So my phi n is a 0. So therefore we can put these two values in this expression, and from this we can write the expression of I0, right? This is in general for REL load. So accordingly we can modify for R load as well. Okay, right. Next, so this is about the resistive load. Next is single phase half bridge inverter with a purely inductive load. Now I have replaced the resistor with the inductor. Okay, right. I don't want to go into the circuit operation. Okay, only important points I will highlight here. Yes, load is purely inductive. Next here, my V0 waveform is a square function, same as that of the previous case. My V0 waveform will be same as that of the previous case. Right? This is V by 2 and here it is minus V by 2. Okay? V0 waveform will be square function, but I0 waveform is a triangular function, and here conduction of the devices will be like this: S1, D2, S2, D1. Here it should be D1, not D2. It should be D1, right? S1, D2, S2, D1, right? And after D1, again there will be the S1. So for purely inductive load, the nature of the load current is a triangular. Nature of the load voltage is square function. For R load also, load voltage was square. For R load, load current was square. For L load, load current is a triangular. Load current is a triangular. Okay, right. Next, for RL load, load is a RL load now. Same circuit, only thing is we have replaced load branch, okay, with RL. Next here, load voltage waveform will be same as that of the previous case. But the thing is here, load current waveform is like exponential rise, exponential fall, exponential rise, exponential fall type of the waveform, right? So please understand these things, okay? Exponential rise, exponential fall. So for RL load, it is this type of waveform. For L load, it is a triangular. For R load, it is a square function. So that's why in voltage source inverter, your load current depends on nature of load. But load voltage for R load, L load, RL load, what is the load voltage? Load voltage is a square function. So therefore, load voltage in voltage source inverter is a independent of nature of load. All right? Yes. So these are the important points. Yeah. Same thing I have written here. In voltage source inverter, the voltage, output voltage wave shape is square function, but whereas output current wave shape, it depends on a load. For R load, it is a square. For L load, a triangular. For RL load, exponential rise, exponential fall type of the wave shape. Okay, they have asked the question, huh? Right, based on this. Next, now in a single phase half bridge inverter, we know the source utilization is only 50%. Okay, that is a drawback of half bridge inverter. So to overcome those drawbacks, we are having the single phase full bridge inverter. In full bridge inverter, we are using 4 switches, S1, S2, S3, S4. Across each switch, a diode is connected in anti-parallel. Okay, right. Here also for R load, you will be getting the output voltage waveform is a square function only. For L load, square function. For RL also, it is a square function. Only difference is, yes, instead of V by 2 and minus V by 2, now that will be V and minus V, V and minus V. Okay, right, because what is happening here, during 0 to T by 2, you are applying the controlling signal to switches S1, S2, right? So suppose if my load is resistive here, suppose this is a resistive load, and if S1 and S2 are in on state, S1 on and S2 on. So what will happen, current will flow like this, V, S1, load, S2 and again back to the V. Like this the current will flow. If you apply KVL, you will get V0 is equal to V, right? So my output voltage is equal to V. Whereas in half bridge inverter it was V by 2, okay? So it is V. Similarly, you will be getting here minus V, right? Plus V, minus V, plus V, minus V, right? So from this, what is V0 RMS? RMS value of output voltage is equal to V. Total available voltage is V, input voltage, and output voltage I am getting V and minus V term na, and RMS value is also V. So my source utilization is 100%. Source utilization is 100%. For resistive load, load current waveform is square function, same as that of your half bridge inverter. Only difference is instead of V by 2R and minus V by 2R, here we are having V by R and minus V by R, minus V by R. Okay, right. So I0 RMS is V by R, and what is the load power? V0 RMS into I0 RMS, which is equal to V square by R. V square by R, right? Next, again for resistive load there is a no operation of diodes, okay, right? Here I will indicate the conduction of the devices S1, S2, S3, S4, and again S1, S2, right? Yeah. Next, merits of full bridge inverter. It requires a single DC supply, 2 wire. Here 3 wire supply is not required, right? Next, which is easily available, okay? 2 wire DC supply is easily available. Next, output voltage magnitude is Vs, so source utilization is 100%, okay, right? 4S is analysis. Now my output voltage is having V and minus V, na pulse. This is V, this is minus V, right? So therefore, my expression in a half bridge inverter, if you recall the expression, it was 2 Vs by N pi. But now my output voltage has doubled, na? So therefore, instead of 2 Vs, now that will become 4 Vs, okay? So 4 Vs by N pi into sine of N omega t, alright? Next, so similarly from this we can write which harmonics are present? Only odd harmonics are present, right? So V01 output voltage at fundamental frequency is equal to 4 Vs upon pi into sine of omega t. So what is peak value? V01 peak 4 Vs by pi. And what is V01 RMS? V01 RMS is peak divided by root 2, na? So it is 4 Vs by pi divided by root 2. So that will be like 2 root 2 into Vs upon pi. 2 root 2 into Vs by pi. Alright? Yeah. This is the output voltage at fundamental frequency. Only odd harmonics are present. Only odd harmonics are present. Right? Next. Similarly for inductive load, yes, what is the change? Same triangular waveform will be getting in the output voltage. Load voltage waveform will be same, that is a square function only. Right? Next, for full bridge inverter, RL load. Load current is exponential rise, exponential fall, exponential rise, exponential fall type of the waveform. Okay, right. So in half bridge as well as full bridge, resistive load, load current waveform is a square. Inductive load, triangular. Inductive in the sense pure inductive, L load, triangular, right? And for RL load, exponential rise, exponential fall type of the waveform. Load voltage waveform is square function only by default. Okay, which harmonics are present? Only odd harmonics are present, right? Only odd harmonics are present. Even harmonics are absent, right? Yeah. Same thing, R load square wave shape, L load triangular, and RL is exponential. This is current waveform. Okay, they have given. Next, now let us discuss the pulse width modulation. So first thing is, what is the purpose of pulse width modulation? The pulse width modulation is generally used to control the output voltage of inverter. Okay, to control the output voltage of inverter, we are using the pulse width modulation, right? But in addition to the controlling the output voltage, it helps in reducing the harmonics present in the output voltage. Okay, so it is used for harmonic reduction as well, right? Next, so which are the different types? Single pulse width modulation, multiple pulse width modulation, and sinusoidal pulse width modulation. Okay, let us discuss first single pulse width modulation. In single pulse width modulation, in the output, we are going to get one pulse corresponding to each half cycle. Okay, one pulse corresponding to each half cycle in the inverter output. Yes, this is the basic block diagram for generating the pulse width modulating signal. Okay, here we are having the comparator. Next, here we are having the trigger pulse generator block. This is trigger pulse generator. Trigger pulse generator means what? This blocks generates the triggering pulses. Triggering means turning on pulses. Okay, right? For power BJT, the triggering pulse is like your base current. For IGBT, triggering pulse is like your voltage, VGE voltage. For MOSFET, it is like a VGS voltage, etc. Okay, right. So triggering pulses. But who controls the trigger pulse generator block? This comparator controls. And what the comparator is doing? Comparator is simply comparing the values of or magnitudes of VC and VR. VC is nothing but the carrier signal. VR is nothing but the reference signal. This is reference signal. Reference signal. And this one is a carrier signal. These two signals we are giving as an input to the comparator. Comparator is simply comparing these two signals, and based on that the comparator will give the output either in form of logic 0 or logic 1. Based on the output of comparator, the trigger pulse generator will either generate the triggering pulses or it will not generate the triggering pulses. Okay, and those triggering pulses we need to provide to the respective switches. Those are present in an inverter circuitry. Okay, right. So here single pulse width modulation technique. This is this rectangular. It indicates my reference signal, and this triangular is my carrier signal. Yes, this is a carrier signal VC. These two signals, right? This is my triangular carrier signal, and this is a rectangular, which is a reference signal. These two signals I have given as an input to the comparator. What the comparator is doing? Comparator is simply comparing the magnitudes of VC and VR. And in the comparator, we need to develop the logic in such a way that if VR is greater than VC, then only the trigger pulse generator will generate the triggering pulses. Means if VR is greater than VC, it is like output of your comparator will be logic 1. And then your trigger pulse generator will generate the triggering pulses. So you can check here from this point till this point, VR is less than VC. If VR is less than VC, output of comparator will be 0. If output of comparator is 0, triggering pulses are not generated. So here you can check VG1 indicates triggering pulses. So no triggering pulses during this interval. If triggering pulses are not generated, means it is like suppose you are having the single phase full bridge inverter. In full bridge inverter we are having the 4 switches na, S1, S2, S3, S4. Right? So triggering pulses are not generated means it is like all the 4 switches are in a off state. Right? So if all 4 switches are in a off state means what is my output voltage? Output voltage will be 0. Output voltage will be 0. Alright. Next, it is VG1, VG2, this is VG3 and VG4. Right. Next, all the 4 switches are in a off state. Right. Next, so my output voltage is equal to 0. Next, from this point till this point you can check reference signal value is greater than carrier signal. So my output of comparator will be logic 1. So my trigger pulse generator will generate triggering pulses. So this is your triggering pulses. From this point till this point triggering pulses are present. So if triggering pulses are present, those triggering pulses we are going to provide to switches S1, S2. So S1, S2 on means my output voltage will be Vs. Output voltage is a Vs. If you are having the single phase full bridge inverter, then output voltage will be Vs. Okay. Next, again from this point till this instant you can check Vc is greater than VR, means output of comparator will be 0. So therefore output voltage, no triggering pulse is generated. So my output voltage is again 0. Right. So similarly from pi to 2 pi we are having the negative pulse. So you can check 0 to pi. That is the half cycle of your output voltage of inverter. Pi to 2 pi, second half cycle, right? So corresponding to each half cycle, how many pulses we are getting? Only one pulse. So that's why it is known as a single pulse modulation. Why it is a single pulse width modulation? Because by changing the value of VR and by changing the amplitude of VC, we can change this width of the pulse. And accordingly, my pulse width can be varied. We can modulate the pulse of the width. So that's why it is a pulse width modulation technique. Now tell me, if my pulse width of the output voltage changes, whether my output voltage RMS value will change? Definitely my RMS value will change, right? If pulse width reduces, my output voltage will decrease. If pulse width increases, my output voltage will increase. Okay, so that's why it is used for voltage control. Okay, voltage control. Now what is the expression for RMS value of this output voltage? Yes, V0 RMS. Yeah, let me write here. V0 RMS is equal to under root 2D by pi into Vs, where 2D is equal to width of the pulse, okay, right. So this is the width of pulse, so 2D is equal to width of the pulse, 2D is the width of pulse. And what is Vs? Vs is the input voltage to the inverter, Next, Fourier series expression, V0 summation over n equal to 1357 up to the infinity. It is 4Vs upon n pi into sine of n pi by 2 into sine of n d into sine of n omega t. This is a Fourier series expression of this single pulse width modulation, okay, right. Now which harmonics are present? Only odd harmonics are present. Right. Next, to eliminate means remove, to eliminate nth harmonic from inverter output, required pulse width is equal to 2 pi by n. So based on this they have asked the question, right. So this is direct conclusion I am writing, okay. I will provide the notes, in that you will find the proof for this, okay. So for nth harmonic the required pulse width is 2 pi by n. So for elimination of the third harmonic, what is the pulse width? 2 pi by 3. 2 pi by 3 means it is like 120 degree, na? For fifth harmonic, 2 pi by 5. If pulse width is 2 pi by 5, 2 pi by 5 means 72 degree. Then the fifth harmonic will be absent in the output voltage, right? Next, multiple pulse width modulation. In the multiple pulse width modulation, corresponding to each half cycle, check here, this is pi radian, means it is a half cycle of my output voltage, and this is pi to 2 pi. Corresponding to each half cycle, we are getting multiple number of pulses. In a single PWM, only one pulse was present. Here we are getting multiple number of pulses, because my VC and VR are like this. This is my VC and this is a VR. VR is a reference signal which is square function, and carrier is a triangular, okay, right. Now we are getting multiple number of pulses corresponding to each half cycle. So that's what is known as the multiple pulse width modulation technique. The width of each pulse is 2D by n. 2D by n, where n is a number of pulses per half cycle, right. Width of each pulse is 2D by n, okay, right. Now I am writing the expression for RMS value of output voltage. Let me write here, V0 RMS is equal to under root number of pulses per half cycle, into width of each pulse upon pi into Vs, into input voltage Vs. This is the output voltage RMS value expression, which is equal to under root, what is width of each pulse? 2D by n into, sorry, number of pulses is n. Number of pulses per half cycle is capital N into, this is 2D by n, width of each pulse, divided by pi into Vs, right? In the examination, they will give you the width of the each pulse, number of pulses per half cycle, okay, and input voltage, and they may ask what is the RMS value of output voltage. So be careful. This is an expression for V0 RMS in case of multiple pulse width modulation technique, okay, right? Next, sinusoidal pulse width modulation technique. In sinusoidal PWM, the carrier signal is triangular, but reference signal is a sinusoidal. Reference is a sinusoidal now. So therefore here we are getting the multiple number of pulses corresponding to each half cycle in inverter output. Check 0 to pi. My inverter positive half cycle completes, but in that I am getting multiple number of pulses. But you can observe here the width of each pulse is not same. In multiple PWM, there also we got the multiple number of pulses per half cycle, but the width of each pulse was same. But here the width of each pulse is not equal, it is a different. And the important point is, if this is pi, this is like my pi by 2 now. What we are observing, as we move from omega t equal to 0 to pi by 2, the width of pulse go on increasing. This is a minimum. It has increased, it has further increased, it reaches maximum. So as we move from 0 to pi by 2, the width of the pulse increases. As we move from pi by 2 to pi, the width of pulse is decreasing. Is it like your sinusoidal waveform? In sinusoidal, 0 to pi by 2 sine value increases, pi by 2 to pi sine value decreases, right? So this type of waveform is more closer to the sinusoidal, because my ideal expectation is to get the sinusoidal waveform, yes or no? But whether my practical inverters are giving the sinusoidal? No, my practical inverters are giving output in terms of square function, means that square function is having some harmonics. So in order to remove those harmonics, in order to control the output voltage, we are using these PWM techniques, okay? So this gives the output voltage which is more closer to the sinusoidal, right? So that's why this is the most effective PWM method, right? Most effective PWM method, right? Sinusoidal PWM technique. Next, now three-phase bridge inverters or three-phase voltage source bridge inverter. In three-phase inverters, we are having the two types, 180 degree and 120 degree conduction mode. Yes, this is the circuit diagram for both 180 as well as 120 degree conduction mode three-phase inverter. We are using 6 switches, T1, T3, T5, T4, T6 and T2. Be careful the numbering like this. This is 1, 3, 5 and this is 4, 6 and 2. Okay, right. Load is three-phase load. It can be star connected or delta connected, and input voltage is a DC voltage. Input voltage is a DC voltage, right? Now in 180 degree conduction mode, 180 degree conduction mode, the important points are, you can check the operation table, right? I am not writing the operation table here. During each interval, 3 switches conduct, 3 switches conduct. Each switch conduct for 180 degree. 180 degree. Okay, we are having the operation table like this: interval and conducting switches. We are having 6 intervals. And during each interval, 3 switches will be in a conduction mode. First interval S6, S5, S6 and S1. Second interval S6, S1, S2. Next S1, S2, S3. S2, S3, S4. S3, S4, S5 and S4, S5 and S6. Like this, during each interval 3 switches will be in a conduction mode, right? And after this sixth interval again it will go to the first interval, right? So each interval is of 60 degree. So 60 into 6 intervals means 360 degree. 360 degrees like one complete alternating cycle of the inverter output, okay, right? Again S1 is in a on state for first interval, second interval, third interval. For remaining 3 intervals we can check S1 is not present na, right? So S1 conducts for 3 intervals and each interval is of 60 degree. So can we say that S1 conducts for 3 into 60 means 180 degree. Similarly you can check S2, here it is S2 present, here it is S2 present, here it is S2 present. So S2 also conducts for 3 intervals. So 3 intervals means how much angle? 180 degree. Similarly you can check S3, S4, S5 and S6, okay. Each switch conducts for 180 degree. At any instant of time 3 switches will be in a conduction mode. 3 switches will be in a conduction mode, right? Now check here, and this conduction sequence is true only when your switch numbers are like this: T1, T3, T5, or you can write S1, S3, S5, and it is like S4, S6 and S2. For this numbering, this conduction sequence is valid. This conduction sequence is valid, okay, right? Next, how is the waveform for output voltage, output phase voltage? Output phase voltage waveform. Output phase voltage for 180 degree square, 180 degree conduction mode, VAN. It is a 6-stepped function. It is like this. This is like pi by 3, 2 pi by 3, pi, 4 pi by 3, 5 pi by 3 and 2 pi. And the pulse, these amplitudes are, or steps are, this is Vs by 3 and here it is 2 Vs by 3, right? Here it is minus Vs by 3 and minus 2 Vs by 3. So nature of phase voltage, output phase voltage is a 6-stepped function. It is 6-stepped waveform. Which harmonics are absent? All even and triple N. All even and triple N harmonics are absent. Triple N means 3 into N in order of 3, which is equal to 3 into N, which is equal to 3, 6, 9, 12, 15, 18, etc. All these are triple N harmonics, okay. So in this waveform, all even harmonics as well as triple N harmonics will be absent, okay, right. Next, so nature of phase voltage waveform is 6-stepped waveform. All even and triple N harmonics are absent in this waveform. How is the nature of line voltage? Let me draw here line voltage waveform. Line voltage is a Cauchy square function. It is a Cauchy square. This type of the function. This is Vs and here it is minus Vs. Pi by 3, 2 pi by 3 pi, 4 pi by 3, 5 pi by 3 and 2 pi. Okay, this is a Cauchy square function. In one of the examination they asked the question, in 3-phase inverter 180 degree conduction mode, what is the peak to peak ripple in inverter line voltage, right? So line voltage waveform is like this, Vs and minus Vs. So peak to peak ripple is positive peak minus negative peak difference. So positive peak is Vs, negative peak is minus Vs. So if I want to take the difference of these two, it is like Vs minus of minus Vs. So it is like a 2 Vs, okay, it is a 2 Vs. Let me write. What is the nature? Cauchy square function. Cauchy square function. Which harmonics are absent? All even and triple n harmonics are absent. Right? Peak to peak ripple in line voltage, is equal to Vs minus of minus Vs, which is equal to 2 Vs, right, which is equal to 2 Vs. All right. So friends, this is about the 180 degree conduction mode. Okay, I think we are running out of the time. Okay, we'll stop here. If you want the notes, you can send me email. Or you can message me. Right, I will share the notes for Genco Transco as well as for your GATE ESC examination also. Okay, right. Okay, thank you. Thanks to all of you.